Hello, everyone. The audio is okay? Can you hear me? Plus,
Yes,
minus?
we can hear you. Yeah, it's perfect.
That's great.
Awesome. So let me just introduce you. Hey, so everyone. So we have Adrian. He's here to talk to us about detecting and analyzing solar panels. So away you go.
Yeah, thank you for the quick introduction. I'm gonna do this screen share now, so we're all on the same page here.
Perfect. Yeah.
Okay. Does it work?
Yes. It's amazing. Yeah.
Okay, perfect. I'm gonna talk for the next half an hour about our research project called Soul AI. It's about solar panel detection in Switzerland using aerial imagery. And I've worked together with Martin on this project for, I would say, about 2 years now, plus minus. So if you want to see, I got this little slide here with our team. So Martin is our professor for geoinformation, and Doni, he's my professor for statistics. And we work on this project together with the Swiss Confederation, especially with the Office for Energy. They have this pretty awesome map layer already, where they have an LOD2, I think, model of all the buildings of Switzerland, containing the various roof surfaces. And out of that, they calculated like basically a shading model to find out how much potential energy is in this roof for solar panels. So this is 3D based, and you can even make a little calculation out of this, how many Swiss francs you're going to earn in this running year if you would use your whole roof with solar panels. So this is the 3D data set that is the basis for this. And a further base for our research was the Swiss Image dataset. This is from the Federal Office for the Topography in Switzerland, and recently they advanced their ground resolution to 10 centimeters per pixel, and you can see, hopefully, on the video transmission, how much of a difference this makes, going from 25 centimeters to 10 centimeters. Those are stitched ortho photo imagery. They are corrected partially, even manually, if there's bridges or really high mountains. So it's a very good data set to start detecting solar panels with. We have these various data models, like it's all coming a bit together, which sets it a bit apart from similar projects. For example, in 2018, there was this publication from Stanford where they already used a type of segmentation network to detect solar panels on Google Maps imagery. This was more for a census type of study. And the difference is now that we have like massively more precise data than this as a background. When we go back to the tasks of object detection, there's these various types of forms that you can get. I'm sure a lot of you are familiar with this already. And what we are going to try in this project is not just a mere object detection, but we want actually instances for every single solar panel. So the base of this workflow comes from the faster RCNN architecture. You might know this already. This is a pretty typical network that draws bounding boxes. This is a past project of mine where we detected animals on thermal drone imagery, but essentially the process is the same. You label a lot of data with bounding boxes, and then afterwards you get nice bounding boxes out of it for with pretty high precision. So we thought this is a good starting point for our solar panels, and we trained a faster RCNN detector for these types of panels, and you can see there's a couple of missing points still. There's a couple of multi overlaps, and obviously the boundaries are not very nice. But in terms of detection, we are pretty good with this already, running at about 92% for photovoltaics, which led us to the idea to use this type of network to identify houses from which we can then get humans to label. But first, I want to show you something which some of you might know already if you were in this conference last year in Mutens in Basel in 2019. I was part of a little workshop where we did the solar panel detection, and I published this this notebook for you. I'm trying to open it quick, because there's a little hack you will have to do when you I hope you can see this now. If you want to do this yourself, you can use the short link. This is the notebook. It should just run through smoothly like that if you want, except for this very first point in Google Colab here. You have to first downgrade NumPy, since this is a bit older code, 1 year old already. There's a version conflict, and this is going to crash the runtime. So you're gonna get a little red warning, and you have to restart the runtime, and then the rest of the notebook will run through. So this just if you want to train your own little solar detector. So this is going to restart the runtime, and then you can perform all the other boxes. And I commented the code, so it should be fairly clear what this is doing if you're interested in doing that. So let's come back to the workflow, or what we what we have been doing since last year was to let trained professional experts specify the geometry of a few thousand solar systems. And then we wanted to train mask RCNN on it. And this is a nice, powerful technology. In our case, we use a ResNet 50 kernel, but we're also experimenting with other kernels. And it allows full instantiation. So we can basically say which panel is which, more or less, like, or at least which field array of panels is which. There was also a cloud contribution client and a couple of other things that were, there was some a code sprint going on in the last GeoPython in 2019, where there's a few cool guys. They coded a few nice functions for us. And then early last year, I think about January, February, we had this labeling workshop where 31,000 polygons were drawn by experts and students. But as you can see, we didn't cover the whole of Switzerland just by labeling it through. There's still a lot of white areas doing that. So this is the images 1 and 2 of almost 8,000. I'm gonna spare you of looking at the rest. But what is nice about it, we get multiple mask outputs from this as PNGs that exactly overlap with the tiles that we generated. One PNG mask specify which category it is, for example, photovoltaic or thermal, or if it was unclear, we also put in the category unclear. And a second PNG instantiates each panel as its own installation. So you can see that here they have all different colors, so this gets encoded as RGB values. If you look at the distributions, like there are few installations that are really large in areas of about 100 square meters per unit, so per consistent area, but the vast majority is actually smaller than 20 square meters. So we were thinking, okay, how do we do this? Masked RCNN, it works well with PyTorch as well as TensorFlow, and we looked at the numbers for both, and it all comes down a little bit to having nice GPU support. We decided to go for PyTorch. It's a great library for machine learning. There's nothing wrong with TensorFlow. I use TensorFlow for past project as well. Just in this case, we thought we're gonna try out to do the parallelization ourselves. I'm gonna come back to this later. So it's quite a Pythonic interface, which is nice, and there's a lot of pre-trained models available, and the optimizers are easy to set. So we had a student of ours having his bachelor thesis here. That was early detection and of avalanches, and he used PyTorch and mask RCNN for this approach, and you can see it works fairly well on this type of. This is not aerial imagery. This is webcam imagery, but basically image is image. So we thought, okay, this is a great source of code where we can base our following work on. And we managed to acquire a really powerful machine to do the inferencing, especially over the whole of Switzerland, which is not exactly I mean, it's a small country compared to other countries, but if you look at the terabytes and terabytes of imagery that you have to put through the inferencing, it becomes a big data paradigm very quickly. So this machine with 192 gigabytes of RAM and 4 Tesla V100 GPUs should do the trick. We are running PyTorch in a Jupyter lab environment, so multiple users can have their own Jupyter notebooks and access shared folders and things like that. And we extended the models that you can find on the internet with this torch NN data parallel command. And first we thought, okay, we're also gonna train on all the 4 GPUs, but it turned out that this is actually still quite a coding effort. So for us, it was more important that we actually can run the inferencing on parallelized platform options, whereas the training didn't take too long anyway. I'm gonna have some data for you right now about this. So you can see how I define here a couple of directories, and that the PNG masks and the object masks are joined with the label masks and then drawn over the images, and you can load all of this into PyTorch and run it. And when you look at the loss graph, this is now a model run with 3 separate classes. So the photovoltaic panels are separate from the thermal installations, or the ones where the labeling experts were unsure. You can see that at about 5 or 6 epochs, so this is this area here in the middle of the graph, you're hitting sort of the glass floor in terms of the loss graph. And glass ceiling, you would say, yeah, but it sinks. So this is about the time that it needs, and we would have 1 or 2 hours per run on this data set of 8,000 images. So that is fair enough. We didn't actually need the parallelism for the training. What was very interesting to see, though, if we pooled the labels together, the photovoltaics and the thermals, they are not even for humans, they are very easy to tell apart, especially also when with this class other, where it's not completely sure. Sometimes you have a glass roof, sometimes you have something that could be a solar panel. But when you pull all of these together into one class, you land up with a bounding box precision of 86%. So this is pretty good, and we have been even able to increase this to about 90% as well now. The segments are a little bit weaker, but I'm gonna explain strategies now how we can increase the precision on this one as well. First, we wanted to plot the statistical linearity between precision and recall, and you can see that the R-square value is really close to 1. So this shows that the model is actually quite good in generalizing the input or the learning effort that we gave. And some well-working results here, just graphically shown that, for example, this dark blue installation in the right bottom here, this is indeed thermal. You can see that as a human by being a slightly narrower and longer and having sometimes like white pipes sticking out of it. And the rest is photovoltaic. That is more easy to see because they often have these metal frames, but not exclusively. There are various types of solar panels, but you can also see that the generated masks, they fit fairly well. Still, we ran into a couple of challenging options. You can see roof windows here. You can see that sometimes the solar panels are arranged in a like sort of triangle setup. So there's more power generated in the morning and in the evening, even though the absolute yield might be a little bit smaller over the whole day. You at least have more distributed power generation of the day, and this type of setup gets easily confused with other roof windows or like these light windows that can be in roofs. So our question was, is it maybe the small panels that are the issues that are easily confused with roof windows? Like, but once we took all the modules or the installations out of our training that were smaller than 3 square meters, precision nor recall increased. So it was, this really wasn't the issue. So we had to go back into the labels and look at them. Especially the ones in the class other are interesting and somewhat difficult. You can see there are some panels that are clearly rightly labeled as such, but because of glare effects and reflection, they look completely different than other panels. And then here's some other installations that are most likely not solar panels. Here, this is clearly a glass roof, but it fits the common type of segmentation that you would expect for a solar panel installation. So we also had to get a couple of experts that actually mount these things to validate our data sets for us. What is a panel, what is not one? Because there's really a couple of difficult scenarios here, and obviously there were a couple of labeling mistakes. So we do have to go back into our data set and clean that up a bit. But let's come to the interesting part of the high performance computing here. What did we do with our 4 million images? Because once we have a good model and we cleaned the labels a bit, it was still a massive problem to run it over the whole of Switzerland. Obviously, you can leave a couple of areas out straight away already, like the lakes. It's unlikely that there's going to be any solar installations there, or the alpine spaces in Switzerland. But the interesting part is now how do you do this efficiently? Because if you would just run it on the CPU, even with normal CPU parallelization with hyperthreading, you would face like 100 days of just, most of it is actually input-output operations, like writing and reading it. And you can decrease this already if you parallelize the GPU usage with it, because inferencing is faster, but it's still continuous running for 1.5 months to do this on 4 GPUs. So our setup here was a job scheduler that actually uses NoSQL or MongoDB database, and then we basically cram the GPUs full with processes for detections. And once the images are loaded and it's all nicely interval spaced by the job scheduler, we actually, this is even an old number, we managed to optimize this down now for a run that takes about ±6 days. So we have some nice improvements happening here by using the NoSQL technology, and it's we have been reducing the inferencing times by increasing the load on the GPUs. If you look at it, there's still, when you look at the memory usage of the GPU and the power consumption, they are actually not completely crammed full yet. the GPUs. You can see this here. There's one is pretty full here, but the wattages are actually relatively low. So we think there still might be potential if we just create more and more and more jobs in time to put this in a GPU memory. And once the image is loaded in the GPU memory, the inferencing runs really fast. Okay, how do we go from here? We use as a kernel ResNet 50 in the moment. There are options to use ResNet 101 or ResNet plus Inception v2. We would either need TensorFlow for this in the moment or change our code to Detectron. Detectron 2 would work for it as well. This is something we're currently investigating, and it seems pretty promising because Detectron 2 is also based on PyTorch. We tried a couple of different sets of optimizers and adapted the learning rate. So obviously you can always label more. But what I still want to leave a few comments on are the post-classification strategies. Because once we get our data out here, we want to process it maybe with Rasterio, Fiona, or GDAL, and actually run multiple models for inferencing. So we can use some type of heuristic measures, for example, edge detections, and or do pixel-wise probability estimations. Why would you go through all of this? So there's a couple of reasons why we need post-classification here. When you use different detection thresholds on the mask RCNN, you get different precisions of the masks. Like, it's pretty clear that what is covered, for example, with an 80% detection threshold, this is definitely a solar panel, whereas with 50% or lower, you might cover areas that are not solar panels anymore. So what you can do is use multiple of these images and calculate an integrative measure for each pixel and say, okay, combined with various other data sets, this pixel has this and this chance of being an actual solar panel. Another critical step for geoprocessing was the labeling boundaries as well as the inferencing boundaries, because right on the edge of the tile, you're going to land up with edge problems like small missing pixels destroying the actual instantiated segments. So one option to go past this is to like shift the type of grid that you're using to tile or to make tiles, or to segment the big virtual raster tile into smaller ones, and shift it by a half vertically and horizontally, and then overlay these images. And together with some edge smoothing and filling operations in GIS, we, or for example, taking the rounding of edges off and making it more rectangular, because this is the general shape of solar panels, we arrive at better masks. There's still some inconsistencies between the cadastral data, which is interesting. This is probably due to the different temporal timestamps of the input sources, but one idea was to use cadastral data together with the other pixel-based information, for example, to validate if something is part of a building at all or not, and then only count these areas to exclude some false positives. I got some graphics here still for optimization, like how we did some tests on the learning rate, and we used different optimizers to generate the bounding boxes. So this gave us another increase of about 2 or 3% in overall precision. And the next step that we're going to take now is to include the near-infrared data into this approach. There's new 10-centimeter data sets available over a large part of Switzerland already, at least the most inhabited spaces, the most populated spaces. And the labels that we have, they are already geolocated, so we can just use them for the infrared data at the same time like we used it for the RGB data. So this is going to be interesting for us to find out where we land with our precision if we use it exclusively on the infrared data, or if we even merge in the post classifier later the infrared data with the RGB data. So an idea would be to do, for example, a pixel-wise random forest classification, use some classic machine learning for that, and say, okay, we got our values from the masks from the RGB training, we got our values from the masks from the infrared training, and together with cadastral data and GIS attributes, for example, knowing that a specific zone is a commercial zone or not, or is in a really steep terrain that would also exclude, for example, having solar panels, then we could arrive at a really fine granular first pixel-based segmentation, but also use it for sub-classification, meaning that we can use our best performing model, which was the one that detects thermal as well as photovoltaics in one go. Use this for deep learning, and then let the random forest decide if it's more likely, based on various different input variables, if it's photovoltaic or thermal. Okay, so that would be the end of my talk, and I'm very happy to answer a couple of questions.
Yes, awesome. So you don't think have anything in the Q&A? Let me also check Discord for any questions. Yeah, you had a slide on that model that is quite good at learning. How did you know this? Do you have a paper on the method you used to prove this?
Yeah, we are we are actually currently writing the paper. So there is something that's going to be published, but we want to wait with the publication before we have a couple of runs that went through the complete Switzerland. We have our first runs now completed, but since we want to use this on multiple data sets still, it would be great to include this information in a paper as well. I don't know which slide you meant in detail now. I mean, you probably meant the overall precision values, and this is something that you can always like try to tweak on and do a couple more optimizations, but I think we're trying to max it out relatively well. Yeah, the publication is coming, to make it short.
Okay, awesome. So we have another question from Terence. He says, "Good job, Adrian. Quick question: what should be the limit of using Google Earth image to detect solar panel objects?"
Again?
What should be the limit of using Google Earth image to detect solar panel objects?
Do you mean maybe ground resolution? So we did have a couple of images in our data set that were still with a resolution of 25 centimeters, and that worked. It was still okay. It didn't work as well as with the 10 centimeter coverage. Trying it out on 50 centimeter data was getting hard. Then it's not really that easy to distinguish it anymore. We were thinking of doing this with infrared data, because that was available early already in 2018 at 50 centimeter resolution, and there the contrast looked relatively high, so this could work, but this is not the general information you're going to have on Google Earth images. So I think Google Earth images is they're getting better every month basically with their data. So I think I would put the limit at about 20 centimeters to do successful solar panel detection and still have masks that are relatively close to the truth.
Awesome. Thank you very much. So the next question, with the availability of 3D point cloud data from surveying agencies, would it be possible to include them to aid the detection in such projects?
I wouldn't see why not. It all depends a little bit on the resolution that you have. Like a lot of the landscape level LiDAR data that gets used for such purposes is at a meter resolution, which is fairly coarse. But what that could help with is, for example, decide on the angle that a roof is tilted at. So if we wouldn't have this beautiful basically modeled data set of the cadastre in Switzerland already, using LiDAR data in a different scenario would definitely allow you to do this task of post-processing and saying, okay, the roof is at this and this angle, at this and this specific spot, so this is that and that likely. For example, solar panels on steep roofs will only be on the south side in the northern hemisphere of a building, or on flat roofs, and that is something you could definitely tell with LiDAR data. So I think, yeah, it definitely has potential to be used. In our case, where we have the high precision 3D model of all buildings in Switzerland, this is so nicely pre-processed for us that going for LiDAR data is would just increase the amount of noise that we have in the data set, I guess.
Cool, amazing. I think we just reached time. Thank you so much for your talk, and thank you for answering all the questions. And also, we just got the last question. Can you share the last slides from the
Sure. I think there's going to be a recording of the whole conference anyway. But I can make an export of a few slides and send you the PDF as a link that in the ML track at Discord.
Yeah, awesome. Yeah, cool. All right.
Perfect.
Cool. Okay. Thank you very much. See you all in the lightning talks part.
Yeah, thank you too.